Okay, so I got everything set up now, finally. Right? So today we're going to be doing the lecture on the Charpy impact, which is the 5th lab. So like Samson said, semester's kind of ending, right? We only have 6 labs for this class, and we're in the 5th one now. And as for grading, I've graded, only your first lab so far, so I apologize for that. My goal is always to grade them each memo within 1 week, and obviously that hasn't happened so far. So again, sorry about that. I'm going to grade your second memos. My goal is by the end of the weekend, so those should be graded by then. But for sure, they're going to be graded before your 4th memo is due, and that's due next week, next Thursday. So not today, but next Thursday. So again, yeah, they'll be for sure graded by then. And I'm going to try to grade the 3rd memo as well, hopefully pretty fast too. But 2nd memo for sure graded by next Thursday. So you can take a look at that feedback. But of course, make sure you look at the feedback for the 1st lab, because I really was, I tried to be very, very detailed on that one. So I refer to that. All right. And then, so today we can't really refer to VKS because there's nothing for this lab on VKS. But we do have this YouTube video here. And, okay. Yeah, just making sure I share on my screen. Okay, so we have this video here that I found from last semester. Well, I used this video last semester to kind of show what this lab was going to look like. So, our test setup looks a little bit different in the lab. So you've probably seen it in passing. We have 2 stations that look similar to this. Right, and this guy, he can rotate this here and he can move this pendulum up that way. We can't do that. We gotta actually move it up ourselves. And I think it's like 60 pounds. So once we're actually in the lab next week, you can do it by yourself. Just make sure you're using good form. I don't want anyone to throw out their back. But ideally, you should have 2 people really that are lifting this up at the same time. So anyways, you lift up this pendulum here, and it's going to lock into place at the very top. And then we're going to release this pendulum, and it's going to move down, and it's going to strike some material that we have down here. So, yeah, there you go. So this is what the material is going to look like in the lab. And you see it's notched here. And so the pendulum is going to be up here and it's going to strike down where this notched part is. Okay, and it's either going to entirely split into 2, or it's going to basically bend quite dramatically at this point right here. So I think this video shows a few different fractures. So you see it's all the way up at the top here. And here, this is a little gauge where we can see how many or how much energy each material has absorbed. So for us, it's going to be in units of foot-pounds. And so again, that's going to tell us how much energy each material has absorbed. So we're going to talk about all of this in this lecture. Okay, let's see if we got... Alright, this is another good thing here. So this is what it looks like in the lab too for this little setup here. And basically you need to make sure that it's as centered as possible. We don't have this little part here which you can do a better job for checking that it's centered. But you're going to do your best to make sure that this is centered. Oh, there you go. Let's go back. Alright, so yeah, there you go. So you see that he broke the material. And then this is how much energy it absorbed. So I think their test setup here measures in joules, so a little over 10 joules. Let's see some fracture. Yeah, there we go. So this is the fracture surface for this particular material that they had. And you see it's pretty smooth for the most part, but it's a little rough, but mostly it's pretty smooth. So again, we're going to talk about all of this today, but this would be an example of a brittle fracture mode. And then I think there's one more that they test, yeah. Alright, so you see this one here, it's about 30, actually 90 joules here. Yeah, so it's absorbing a lot more energy. And so now if you look at this fracture, look at that, I mean, it's totally different. So now it's a lot more rough, right? And it's not this clean cut, it didn't even fracture into two different kind of, what's the word? Two different kind of lengths here, sections, whatever. It stayed in one whole piece, but it bent, you know, for the most part. And it's a lot more rough again. So that's because it absorbed a lot more energy. Alright, and then you can compare the two here. So this one on the left, I don't know what material this was. I didn't see it in the video, but this one absorbed a lot more energy, and because of that, it didn't basically fracture into two sections like this one on the right. So the left one, we got a ductile fracture mode, and the right one is a brittle fracture mode. Alright, so that's what we're doing in this experiment. And then what we're going to do in the end is make a graph that looks similar to this. And we're going to talk about all of this. So you see that there's a range of temperatures here, which we're going to be doing in the lab. So in the lab, we have 3 different materials. We got aluminum, like we always have. And then we have 2 different steels. I forget which ones they are this time. I think one of them is actually different from what we've used so far in the labs. I can't remember off the top of my head. But we're going to construct this graph where basically once we do the test, we have this range of temperatures that each material is subjected to. So we're going all the way from liquid nitrogen on the cold end, all the way up to baking in an oven. So we have, I don't know, maybe 6 different kind of temperature modes. So we're going from, I actually think I might have it in my notes here. Let me check. Yeah, okay, so we have 6 different temperatures that we're going to have each material in. So we have liquid nitrogen, and then dry ice, water ice, so just ice and water. And then we have room temperature, boiling water, and then an oven. Okay, so we're going to have those 6 different temperatures for each material. And basically, you're going to take it from that environment, and as quick yet as safely as you can, you're going to move that material onto the test stand, and then you're going to run the experiment. And you want to be quick, because if, let's say we have dry ice and you're kind of slow, it's obviously going to be warming up to the temperature of the room. And then we're not really testing it at that temperature of dry ice anymore, so there's going to be error there. So you want to be as quick yet as safe as you can be when you move it onto the test stand. Alright, so that's what this experiment looks like. So again, we'll be doing this next week. And I think it's actually a pretty fun lab. It's certainly more involved than the last lab, right? The column, that was honestly kind of boring compared to past semesters, just because all you guys did last time was press play. That was really it. So it wasn't very exciting. But this one, it's a lot more involved for everyone. You know, you got to do everything yourself this time. You know, there's no play button here. You got to set up everything by yourself and then run everything by yourself. So it's more exciting. Okay, so that's what it looks like, and then we'll start the lecture. Alright, and this is a pretty fast lecture too, by the way, just a little heads up. I think the column is probably the most involved for the lecture and then for your lab report too. At least for the data reduction, right? I don't know if I think only one person so far has turned in the memo for the column, so that was pretty fast, to be honest. So I don't expect most of you to have done it already, but the data reduction for the column is probably the most involved, just because we have those 3 different test setups, and then each test setup has 12 columns each. So yeah, that one is more involved than the rest. And also, by the way, the results I've seen so far from all of my sections for the column, not great, and that's not a knock on you guys, but it just hasn't been very good. So when you see the results and you see it's like a really bad graph, comparing the theoretical to the experimental, the curves might be kind of crap, to be honest. And again, that's not a knock on you guys. So we had the issue when our groups for pin and pin fix, we didn't use the pin support. That's a huge blunder there, right? I didn't notice that myself, so a lot of that is on me too. And because I didn't notice that, and you guys didn't notice that, the lab procedure didn't even show that part, so that's why we all didn't catch that. But because we didn't have that pin support, that's going to be a big source of error. So you should talk about that in the report. But even besides that, the fix results, from what I've seen from at least my other sections, they haven't been that good either. And it seems like you guys all did the experiment quite fine. So a lot of it, though, what I've noticed in the 3 sections is some of the materials, they were already like kind of bent a little bit. And that's only for some of the materials. It wasn't for all of them, but really, so when you guys do your memo for the column, try to really think back to the lab. I know it's already been a week now, but think back to the lab, and if there was anything that you remember, like a material was already a little bit bent, or maybe the ends of the material, they were kind of cut, kind of diagonally instead of a clean horizontal cut, then it's not going to seat as well on the end supports. And then you got, if it was a fix end support, sometimes those are a little bit crooked. I actually saw that on one of the stations for sure too. So if that end support is a little bit crooked, you're not going to have this completely straight compressive axial load. So that's going to mess things up. So there's a lot of different sources of error for this experiment. So you should, think about all of that when you make your report. So just thought I'd mention that. Okay, but for today, again, we're doing the Charpy impact test. Alright, so as you saw in that video that we kind of took a little bit of a look at, we have a pendulum that we're going to be raising up to some height, so there's a lot of potential energy there. And then we're going to release that pendulum, and it's going to strike a material or a specimen that we have, and then it's going to fracture it. And it might be a clean cut, or it might be just kind of bent, basically bent in half like you saw for one of those materials. It depends on how much energy that it can absorb. Alright, and also we're going to be doing this at a variety of temperatures, 6 different temperatures. Okay, so 6 different temperatures, and you know the purpose of this is to see how much energy each one can absorb. Alright, and the big thing here, so we're testing 3 different materials. They're going to behave differently. So you're going to see for aluminum, throughout this temperature range, aluminum can actually absorb just about the same amount of energy throughout that entire range. But something like steel, at the very low end, so very low temperature, it can't absorb very much energy, but once you get hotter and hotter, it can absorb much more energy. So, you know, these different materials, they behave differently at different temperatures. So that's the big kind of takeaway for this experiment. Okay. Alright, so because we have this pendulum and we're releasing it from our top height and we're going down, that is going to be an impact test. And that's, you know, very different than what we've been doing so far. So, you know, so far the software that we've been using, we actually set the test rate, right? It's usually, and the machine, it does this by having a constant deformation rate. So usually we set it at 0.01 inches per minute. So that's really slow, right? We're deforming at a very slow rate. But for this test, now it's not 0.01 inches per minute. It's just, you know, boom, right away. It's an impact. So it's, you know, in a fraction of a second, we go from being in equilibrium and it's all chilling to being fractured. So, you know, the takeaway for that is instead of having this very slow strain rate, it's very fast this time. I just noticed, you know, when I was talking before, I saw a little symbol for my pencil. I've never seen that before, and I thought I was tripping out, but now it's gone. Anyways, I don't know what that was for. I've never seen it. Okay, so past experiments, the strain rate very slow, and it was controlled. It was set at 0.01 inches per minute. Alright, and then this experiment, it's going to be just a very fast, sudden strain rate because it's an impact test. Okay. Alright, so again, the big takeaway for this lab is to see how much energy is absorbed for each material. And this energy that is absorbed, you know, that's called the impact toughness. So you might talk about that in your 331 class, your stress mechanics class. Hopefully you do. Alright, and this impact toughness, you can actually calculate it. If you have a stress strain curve, it's the area that's under the curve. Now for us, we're not going to calculate it that way. We just have that dial gauge in our test, and that's going to directly tell us what that impact toughness is or how much energy it's absorbed. Because, this is an impact test, so we can get it right away once we just look at how much energy it has absorbed from that dial gauge. But if you do like a tensile test or something, you can calculate the impact toughness that way by looking, or really the toughness would be a better word that way, by calculating the area under the curve. Okay, so again, for our lab here, since there's very little strain that's going on, or at least the time is very, very short, we're not going to use that method for calculating the area under the curve. That's just not reasonable at all. But again, you might see this on a stress strain curve. So here we have a stress strain curve. So we have strain here, and we have stress here, and this will be just to highlight basically something that isn't tough and something that is tough. Alright, so we got 3 different materials here. So the material in blue and the material in red, they're very different, right? So the material in blue here, it has a very high UTS value, so it can take quite a lot of stress, but there's not a lot of strain, right? So this would be something like a ceramic material, or you can have like glass or something. So it's strong, but it's a really brittle material. It can't deform very much at all. All right, and then we have this in red here. It can't take that much stress, but it deforms quite a lot. So for that, I guess, look at my notes here. This would be like an unreinforced polymer. Really, I think a very drastic example would be something like or rubber. And deform it quite a lot, but it can't take a very high amount of stress. And then in green, we can absorb. We're kind of here for the amount of stress that we can go, and it can still. I shouldn't actually have drawn this quite as far. Let's draw this again. I'm lagging. I don't know why. Let me change my Wi-Fi. Okay, is it better now, or am I still lagging? Okay. Alright. I'm gonna leave and I'm gonna come back. If you can. It's better now? Okay. Yeah, so my voice is through my laptop, and the Wi-Fi seems a bit crappy lately. So, hopefully it stays okay. Okay, so tell me again if I start to lag, though. Okay, so again, talking about these three materials. Stress that we can undergo and a reasonable amount of strain. And if you calculate the area under the curve here, what am I lagging again? Oh my gosh. Okay, I'm gonna leave and come back. My mic was muted. Okay, so am I lagging right now? Upload speed I was saying was it's 25 megabytes per second, so it's okay, but yeah, Wi-Fi's been kind of crap lately. Okay, so if I lag again, I don't know, maybe I should just record a video afterwards because it's kind of unusable to be lagging in class the whole time. So yeah, just keep me updated if I start to lag. So let me say one more time. In blue here, we have a very strong material, but it's we can't undergo quite a lot of strain, so it's a brittle material. And then in green here, it's kind of like our past labs have been. So, think about like 1019 steel or 1045 steel, maybe aluminum. We can take a decent amount of stress here, at least relative to these other materials, and we can take a lot of strain as well, or at least a decent amount of strain. And then at the far end of the spectrum is the one in red. It can't undergo very much stress at all, but it can deform quite a lot. Alright, and if you're going to calculate the area under the curve for all of these materials, the one in green has a much larger area. So the one in green has the highest impact toughness. Or in this case, it has the highest toughness to be more generic. That should say red, not green. Okay, so that's kind of a little recap on toughness. And if we kind of think about, I guess, in everyday kind of life, if you talk about a brittle material, that means that it can, usually it can be pretty strong, but it's not going to undergo a lot of deformation. So, obvious one would be something like glass, right? It's usually pretty strong, but once you break it, it's going to shatter, and it's going to be very sad if it's your phone. On the other end of the spectrum, if you have a ductile material, that means it's not very strong, but it can deform quite a lot. So that would be going back to the example of, very far into the spectrum, but something like gum or rubber, we can stretch that quite a lot, but it's not very strong. So that's kind of the everyday life kind of definitions that we have for ductile and brittle materials. But in this lab, we don't want to really kind of have that narrow frame of mind. We need to be more generic when we talk about a ductile or brittle fracture mode. So that's the keyword, the fracture mode that we have. Because depending on the temperature that the material is in, it might behave like a ductile material or like a brittle material. So instead of just having, that all-encompassing term of brittle or ductile, that's kind of narrow-minded. We want to think about the fracture mode that it's kind of undergoing. Okay, so again, the fracture mode that we have, it can be either ductile or brittle, and this is going to depend on the material and the temperature. So if we have something like copper or aluminum, basically it's going to behave ductile throughout that range of temperatures. So it's going to be able to absorb quite a lot of energy from going from a low temperature to a high temperature. But if you have something like steel, that's going to behave differently. So at a low temperature, steel is going to behave like a brittle material. At a high temperature, it's going to behave like a ductile material. All right, and the kind of go-to example here, and I stole this from Dr. James, just to be clear. Who knows who he may have stolen this from, but go-to example is the Titanic. So I guess that was made out of steel. Doesn't make sense, but the Titanic, right? So it was made out of steel, so at hot temperatures, it was fine, it was chilling, and, it was strong. But at low temperatures, meaning when there's icebergs around, and it's really, really cold, that steel started to behave like a brittle material. So when you hit an iceberg, and the steel is behaving like a brittle material, you're kind of screwed, and it's gonna break. It can't absorb very much energy at impact when they hit that iceberg, and because it's behaving like a brittle material, it breaks. It actually, it was splitting it in half. Actually, no, not the Titanic did eventually split in half, right? But there's also another example. I think it was like some U.S. naval ship. If you look this up, it split in half just in cold water. I don't think they even hit anything, but it just split in half in cold water because that steel was behaving like a brittle material, and because of that, it split in half, which is insane. All right, so this is why we learn this stuff, and we can take that information and know that, okay, if we have a ship made out of steel, maybe we shouldn't go into cold water, unless you should reinforce it in some way. All right, so now we're going to talk about another important thing for this lab, which is actually going to be one of the deliverables, and this is the ductile to brittle transition temperature, so DBTT. Okay, so it's kind of a mouthful to define, but this is going to be the temperature for which the impact energy is halfway in between the impact energy for our highest temperature and our lowest temperature. Okay, so let me write all of that out and then we'll kind of break it down a bit. At least when I first saw this definition, it's just, there's a lot going on. Okay, so an easier way to think about this, let's make a graph here. Alright, so our graph, we're going to have the impact energy on the y-axis, or the basically the energy absorbed on impact. Okay, so that's going to be in units of foot-pounds, and the temperature is going to be in Fahrenheit. And if we make a graph here, I'm going to draw a very kind of extreme example here. Okay, so you might get a little S-curve, a little snake here. So at these very low temperatures, we aren't absorbing much energy at all. And once we get higher and higher and higher, at the very high end for the temperature, we can absorb quite a lot of energy. So at low temperatures, it's not very tough at all. At high temperatures, it is very tough. And you can see that, again, this is a very drastic example here. But there's, at some point, we're having this very large increase in the impact energy. And that kind of transition point is the ductile to brittle transition temperature. Okay, so to me, it's always kind of weird. We're going from right to left if we're saying ductile to brittle. Because we're absorbing quite a lot of energy on the right-hand side, and then we're going to the left-hand side where we're absorbing very little, so we're going from ductile to brittle. I don't know, just the opposite of what we always do, right, from left to right. So anyways, that temperature right there, that's the ductile to brittle transition temperature. So, to do this, to kind of calculate it or find it, we're going to look at the impact energy, our highest impact energy, and then our lowest impact energy. We're going to take the average, we're going to look at that impact energy, and then we're going to use that to find the temperature at that impact energy. Okay, so we have like our 2 points in purple here. Take the average, and we'll go out to find that intersection point with the curve, and then we can find our temperature that way. And again, that's the ductile to brittle transition temperature. Alright, so this one was very defined. So this might be something kind of like steel, but not every material is going to be like this, where it's not going to be as defined here. So this one, again, is a very defined transition temperature, but not all of them are going to be like this. Probably most of them won't. And this is why we actually have this method to find that transition temperature, but it's more like a range then, right? If it's not this drastic graph here, it's more of a range for when we're transitioning from ductile to brittle. Okay, so if it's not this kind of well-defined transition here, in that case, you might be kind of having a mixture around this region of being both a brittle material and a ductile material. So instead of either having a clean cut, that's a brittle fracture mode, or a very rough kind of bending going on, a ductile material or ductile fracture mode rather, you might have a combination of both of them. Depending on the material and depending on the temperature at which it fractured at. Okay, and this part here is just more of just for you to know. It's not really part of the experiment, but ideally we want this transition temperature to be really low. And then we would be operating at a higher temperature than that. So if it's a really low temperature, then it's only going to fracture at those low temperatures. Okay, or it's going to transition to a kind of brittle fracture mode at low temperatures. So, typically we're not operating in really low temperatures, but if we are operating at really low temperatures, I don't know, you're in Siberia or something, then, you should choose your material wisely. So it might be something like aluminum, where it's going to behave as a ductile fracture mode even at low temperatures. But again, for the most part, for design choices, you want to make sure that your operating condition is higher than that transition temperature. That says average. Yeah, sorry. Bad writing. Okay. Alright. That's good. And so our kind of last part here, we're going to talk about the different material structures. So for this part, I'm going to be honest, I don't really know much of anything about material structures. I think we have a class here on campus for this. I forget what it's called, but I know I've had some students in the past that have taken this class. So, you're going to talk about a face-centered cubic structure. I got to look at my notes. A body-centered cubic structure and a hexagonal closed pack structure. Not FEA. You might talk about it in those classes. I'm actually taking a grad level FEA class right now. We haven't talked about them. But there's one class specifically just for the structures of materials. So yeah, it's not FEA, but I forget what it's called. So anyways, for this, I'll draw out a graph, and then we'll kind of highlight which curve corresponds to which kind of structure. Yeah, I don't know if they offer this class every semester too. I haven't seen it that often, but yeah, I forget what it's called. So I think this part, it's good to know, especially if you actually have knowledge on this stuff, at least more than I do. It probably makes a bit more sense, to be honest. But for our lab, we're not going to focus on the structure, the actual kind of crystalline structure of all the materials. We're not going to focus on that. We're just going to focus on the behavior of each material at these varying temperatures. So we're going to focus on for aluminum, how does it behave at very low temperatures versus high temperatures, and steel. I think we're doing a 1018 steel. It might be different steel, so 1018 and something. We're going to see how that behaves at low temperatures and high temperatures. And then we're going to see the transition temperature for each one. Okay, so in blue or in purple here we have FCC, so that's going to be, I'll write all this out in a second. This will be a face-centered cubic structure. And then we'll have one in green here. Okay, so the one in green is like we had up here. We have this kind of S-curve. Okay, so that's a body-centered cubic. And then we have one more, which will be in red, and so I'll just put this one down on the graph, but we're actually not going to see this one in the lab. Okay, so this one in red, it's it can't absorb very much energy at all. Okay, and we're not even really talking about the structure of the material, but we have high strength alloys down here, so they can't absorb very much energy on impact. So these ones are going to be more brittle fracture modes down here. Okay, but for purple and for green, we're going to focus on those because that's what we're going to actually see in our lab. So in purple, we have FCC, that is a face-centered cubic structure. Okay, so for these FCC materials, or I should really say structures, materials is fine. So there's a very small decrease in our toughness as the temperature goes down. Or I should label my graph. That'd be better. Okay, so we have temperature on this axis, and then our y-axis, that's going to be the energy absorbed on impact. Okay, so again, in purple, just looking at this graph, if we're at a very high temperature, it can absorb quite a lot of energy. And then as we decrease our temperature, even drastically, so this is, for our lab, going from an oven temperature all the way down to liquid nitrogen. So very big difference in temperature. it's still going to absorb kind of relatively around the same amount of energy. So that's, I don't know, to me that's pretty crazy, but we'll see that for, I think it's aluminum for this lab. I'm pretty sure it's aluminum. Yeah, it is. I forget which type of aluminum offhand. It might be 6061 T6, but we're going to specify in the lab. Basically, we're going to, what we've done in the past, you don't need to do it, but we've wrote kind of like a graph on the whiteboard in there, where we have each of our three materials, and then we have the differences in temperature, and then we write down the energy absorbed on impact. But anyway, so these purple materials, their toughness is pretty, I guess I shouldn't say constant, but it's very similar throughout this range of temperatures. Okay. And so these would be good for low temperature applications. Of course, you got to keep in mind what kind of strength you need for your application, but in general, if you're working in a really cold environment, you definitely want to use one of these materials because they're not going to fracture as easily at this low temperature. No, oh really? That's funny. I haven't even seen that movie, to be honest, but kind of engineering in a movie, huh? Does kind of make sense, though. Okay, so yeah, face-centered cubic structures, again, they're good for low temperature applications, and copper and aluminum. So we've talked about aluminum, but also copper is another really good example here. And we'll actually see the kind of ductility of copper in the very last lab. So that's the double shear lab. You'll see just how ductile that material is. It stretches quite a lot. Okay, then the next one is going to be our body-centered cubic structure. Is it Ant-Man? Is that from Marvel? Okay. Okay, so body-centered cubic. For this, looking at the graph again, these are going to be materials where we have a very sharp transition point. So we're going to have this kind of rapid change for the amount of energy absorbed, meaning going from ductile to brittle or from brittle to ductile, however you want to think about it. It's going to be a very sharp transition. Okay, so examples, we have steel, so that's what we're going to see in the lab. And so, just looking at this graph, you might be like, shouldn't we always choose FCC because it absorbs more energy on impact? But this isn't, this is only for toughness, so it's not going over the strength. You see down here, it's not very, very strong, or sorry, it's not very tough, these high strength alloys, but they are very strong. It's like our graph that we saw up here, our stress strain curve. We can look at the toughness from a stress strain curve by calculating the area under the curve. So the one in blue here, it's very strong, but it's not very tough. And then green, not quite as strong, but it's really tough. And then in red, really not strong and really not tough. But it can deform quite a lot. So you gotta, keep all these in mind if you're looking at kind of what application you want to decide on a material to use. So our body-centered cubic materials here, again, they have this very well-defined transition temperature. So we want to be sure that we're above that transition temperature in our applications. And it's going to be really brittle at the low temperatures, so make sure you're not, in the Antarctic down here. And an example would be steel. So again, for our lab, we're going to be looking at this purple curve and this green curve. So purple, that's going to be aluminum. And in green, we have two different types of steel. And, maybe it is 1018 steel and 1045 steel again. Again, I just can't remember offhand. But we're going to see these curves in purple and green for the lab. Right? And then the fracture appearance, we're going to be taking a look at that as well. So just like we saw in the video in the beginning of class, if we have a material that behaves as a ductile fracture mode, it's going to be this very rough, very jagged appearance for when it fractures. It's just going to bend, and it's not going to even have a clean, or it's not going to fracture into two, right? It's just going to bend very forcefully, and you're going to see that it's very jagged and rough. And in contrast, a material that behaves as a brittle fracture, that's going to be a much more kind of clean-cut surface. It's going to split into two, and it's going to be very clean-cut. Alright, and we're going to take pictures of that. At least we have in past semesters. So there's a good kind of macro camera in the lab, and I imagine we're still going to use that. So, some people, they'll be running the experiment with the pendulum, and then some other students, you're going to take pictures right after it fractures, and then you're going to put that in the report, and that'll be part of your kind of results and discussion, talking on that fracture appearance. Alright, so let's see if there's anything else to talk about here. No, not really. Okay, so that's the lecture for today. So again, it's a pretty simple lecture. All we're really looking at is the amount of energy that we absorb on impact. And then we're going to make these graphs. And, you're going to talk about that. Alright, so that's it for the lecture for today. Some reminders, though, before we end. Your fourth memo is going to be due on next Thursday. And I'm going to be doing my best to get your second memo graded by the end of this weekend. Yeah, I can do that. I just got to finish my midterm project by the end of tomorrow. But once that's done, I'll be grading basically all weekend. So I'll try to get that second memo done by the end of the weekend, and then I'll start grading the third one as well. But you will for sure have your second memo graded before the fourth memo is due. Alright? Watch Ant-Man while I grade. I'll probably be... I imagine there is a baseball game on the weekend. I'll be like watching the World Series then. Yeah, man, go Braves. I know we talked about it before. Do not want the Astros to win. Alright, so anyways, that's it for today. Hopefully you guys have a good weekend, and I don't know. Do you guys have midterms now? I don't even know, to be honest, but whatever you got going on, hopefully it goes well. And I'll see you guys next week in person. Alright, have a good weekend.
Thank you, Professor.
Yep. Alright, see you guys. Anthony, okay. There he goes. Bye bye. Okay.